This is a continuation of the global winds and pressures, and you should have by now seen the video that I created, which I drew out a whole diagram of winds and pressure systems. And from that, then I want to expand a little bit here. So let's look at what we see, for example, January in the world. And if you have that other diagram kind of in mind, at least, I would recommend you might go back a bit and maybe draw it out in brief, so you have it to study and just kind of be more familiar with. And if you don't have that, maybe you should just go do that. Go ahead and draw that out, or print out what I had at the end if you have a way of doing that, and then have a look at that. Compare with what I'm going to talk about now. If you don't have that in front of you and you're looking at this map with me, you're not going to really get much out of this probably. So what we see here, this is January, so it's winter in our hemisphere. We see that subtropical high, one off of the southwest coast of Europe and North Africa, the other off our own southwest coast. And you also see these subtropical highs in the southern hemisphere. So in the real world, there's not just one set of these, or one of these in either hemisphere, but in fact various. And so that general model just gives us an idea of how things work. And you can also see those subpolar lows, like one up here and off of Greenland up in the northern hemisphere, and then the Aleutian low, sometimes it's called, depending on where it is, that's off the Aleutian Islands there. Sometimes it's over here. These are just average locations of these pressure features. And so this, and then you can see the increasingly higher pressure as you go down here in the southern hemisphere, closer to the South Pole, even in what's their summertime down there. And this is our winter down here. This big low pressure subpolar low here kicks a lot of storms off into Europe during their winter time, their rainy season. And on the other side over here, this low pressure cell, depending on where it is, but can kick off a lot of weather activity, especially in our latitudes. That's where we get our wintertime rainy season. I'm speaking now in April, and there's actually a big low right about here right now, and then we've got some high pressure near the coast, so not all that unusual, even from January. But these things change slowly. So if you look at the next slide, then you can see, just looking at those subtropical highs, see how that moved up? And that zone of low pressure is gone, right? Nothing there. There's a little zone of low pressure here. They didn't put an L on it up here off of Greenland. But it's active enough from the Greenland ice sheet that it does kick up storms. And so if you're in a place like, say, Bordeaux, France, right about here, same latitude as the Willamette Valley, 45 north. But their summers, they get about 4 times as much rain in July and August as we do from that low pressure cell up there, even though it's not a real strong one. But the subtropical highs are here much stronger, dominate much of the ocean basins. And you can see those again featured down here in the southern hemisphere. And so this has all moved north a bit, with the sun moving north as well. And you can see, where is it windiest in the world? If you look, what's the broad latitudinal windiest place in July? It's easy to see that, isn't it? See how close those isobars are spaced down in the southern hemisphere? My gosh, this is just amazing. Look how they're packed. If we go back to we'll find out that the one in January is even more intense in some spots, but very more of a restricted latitude. So back to July, that would be their winter down there. An enormous area of very strong westerly winds form across this zone here. This is a nice little animation. It's only about 2.5 minutes. Does what I did on my kind of Khan Academy style sketch it, where I drew out the winds and pressures. This is a nice professional animation. You don't have to spend a lot of time with it. I strongly recommend you view that several times and maybe come back to it again before exam 2 to get really, really familiar with how that works. Everything he says there is right on. For the most part, it is stuff that I emphasized as well. So that's a great animation. I'm not going to play it here. The audio gets a little messed up sometimes when you do that. So I don't want to waste your time with that here, but definitely go back and look at that. That's gold mine for you for exam 2. There's some stuff in there definitely want to understand well. So in looking at those high and low pressure areas that we described and that you just saw in that, hopefully in that animated video that was in the previous slide, there's The equatorial low pressure zone, also known as the intertropical convergence zone, what do you need to know about that? It's a zone of cloudiness and abundant precipitation. One of the things that we'll learn is that equatorial regions, with only a few exceptions around the world, are very wet places, whether it's the Amazon, whether it's much of South East Asia, offshore, very wet places, Philippines, and so on. These are dominated by that low pressure zone. Convergence there, very warm, humid air, and lots of precipitation. And again, that is formed because of thermal reasons. It's very warm in those regions, the warmest parts of the world on average. So you have that convergence around that warmth. The flip side is the thermally generated polar high pressure cells where air subsides instead of rising, as we drew in the diagram. And these, especially when those high pressure cells are strong, they're associated with very minimal precipitation. And again, thermally induced in this case, the cold, very, very cold air sinks over cold surfaces. The subtropical high pressure cells are dynamically induced, as we said before, meaning that it's not direct thermal induction, but rather rising air over the equator settles over the subtropical areas. And so that movement of air itself creates the cells rather than the cells being created by extreme surface conditions. So typically the dry climates, especially on the west side of continent, some of the world's driest deserts, the Baja Desert of Mexico, for example, is one of those. And it's an area that's more or less dominated by subtropical high pressure much of the year. And then finally, the other dynamically induced cells, not because it's cold or it's hot, but because we have air converging into them, those subpolar low pressure cells, the polar easterlies and the westerlies converge into this area, and they cause our wintertime storms. Those are referred to in meteorology as mid-latitude cyclones. Cyclones isn't a term in everyday speech that we tend to use, but in meteorology and climatology, that's what they're called. Again, converging air from the polar highs and the westerlies. And this is a zone typically of kind of foul weather, whatever time of year you're there, but especially in the wintertime for each respective hemisphere. So all of those, as I mentioned in my animation, move north and south in response to seasonal changes in the subsolar point. And the wind systems do the same. So in other words, the intertropical convergence zone moves north and south. The high pressure cells move north and south. As I speak in April, we're moving into our spring and eventually summer, and the Pacific High is moving up north already, and it's kind of made an early appearance here for those of you listening to this this spring of year 2020 to mid-April. We've had really summer-like weather already from that. The primary wind systems then that flow from those cells, just to know these characteristics, the trade winds are the most constant, and they're also the region where tropical storms and hurricanes form. Those are the trade winds. So not quite equatorial typically, but definitely tropical for the most part, and an area where you'll see those powerful hurricanes eventually form. They often end up outside that zone, but that's where they start out. The westerlies, here's an interesting one. Their intensity is positively related to equator polar temperature differences. What do I mean by positively related? In other words, the westerlies are stronger when there's a big difference between the equator and the polar temperature. So when would the biggest difference happen? Initially, you might kind of pause for a moment and you're not sure the answer to that, what time of year. But if you think about it, the equator temperatures are pretty much constant year round. So when you look for a big equator temperature difference, it has to be then during the wintertime when the poles get really cold. So that's when the westerlies are strongest. So our winter time. So November, December, January, February, into March. That's the time of year when they're the most wound up and the strongest. Okay, so the winter low sun season is when they're kind of peak strong, and they are the most persistent and strongest, interestingly, in the hemisphere where the equator polar temperature difference is the largest. Let me say that again. Which hemisphere is it where the equator polar temperature difference tends to be larger? Is it the northern hemisphere or the southern? Now, if you think about it a little bit, the southern hemisphere always covered by ice. It is always cold, but definitely colder in the winter. That is the hemisphere with the greatest difference. And that's where we saw all those isobars stacked up in one of those earlier pressure maps. And we said, wow, that's the windy westerly zone. There it is, southern hemisphere. So for your studying, they are more persistent and strongest in the southern hemisphere, and they are strongest during the respective winter of each hemisphere. All right. So polar easterlies, because it's a zone of sinking air that where basically no sunshine, very cold surfaces, the air sinks dramatically there. That's what high pressure is. Those polar highs then are from the air, are in the areas where the polar easterlies flow out of them. Basically, that air is sinking at the ground and flowing out and coming from the east. Stronger in the winter because that's when it's coldest. The polar front, not something we put on the diagram, but it's a boundary where the polar easterlies and the westerlies converge, and wherever that happens to be, and it does change its location, we have a bad weather zone there. The actual global wind circulation is modified by the effects of continents and their different levels of heating and cooling as compared with the oceans. Okay, so there's some complexity in that, and we'll talk a little bit about that eventually, but that's not something I want to spend a lot of time on here just because we have so many important things to do. Just to give you a sense of the power of the Southern Ocean and down off of Antarctica, north of Antarctica a little bit. They have an annual sail around the world, maybe it's every couple of years, sail around the world race. And this gives you an idea of the size of the seas here. Pretty amazing conditions there. These professional sailors and it's kind of a rich person's sport, but if you've ever watched it, just go sail around the world race, the Volvo sail around the world race on YouTube. It's kind of mind-blowing the conditions they're in that Southern Ocean of those persistent westerlies. Really, really powerful zone. If we just had electricity lines, we could power the whole world easily from a very small patch of that Southern Ocean. Fortunately, there's enough wind in the other hemispheres to work for us too, though, so that's not a problem. The general atmospheric circulation, this is kind of like the one that we drew in our little animated video that I put together. But this is a little more complicated. But if you just look at the general thing, I got the subtropical highs here, got Mortem down here. You've got the trade winds. You got this whole convergence zone where those trade winds meet, and you have rising air. Cloudiness there, which would actually extend across this whole area, but that's just kind of shown here as a cross section. The sinking air of the subtropics, sinking air, and then this kind of polar front region kind of gives you a sense of how that actually looks in the real world. Not too unusual. This would be that looks like more of a wintertime pattern to me, although the polar front isn't as far south typically as it would be in the winter. But the subtropical high location is a little on the south side. So I would say that's typically a winter thing. But it could be late fall or early spring as well, I think, looking at it. So the upper atmospheric circulation is where we have jet stream and the core of the upper level westerly geostrophic winds. We talked about those that flow parallel to isobars, generally high velocity winds. Within that, and this is very important in the whole world of climate change science, is there are Rossby waves that form in that circulation of the jet stream. And these are very high amplitude waves becoming more common, extreme, and persistent as the Arctic warms. And what that's doing is it's reducing the polar equator temperature gradient. And so what it does is just kind of gives crazy weather to us. And there's an animation to look at on that as well. So I'm about out of my 15 minutes on this particular one, but we'll be doing more later.